This is the lesson video for 6-2 Day 1. You have handout to go with it. First, we have to talk about some notation back from pre-cal. You use the sigma notation in pre-cal to take sequences or series and sum them or add them all up. So in pre-cal, if you'd seen something like this, you would have realized that this function right here generates values. So starting when k is 3 up until when we use k of 6 and every value in between, what we'd be trying to do is add up all the values that came out of this. We'd be trying to add up when k is 3, the value of that sequence is 6. And then we'd add the next value when k is 4, which according to that equation would be 8, or that function. When k is 5, we'd get 10. And finally, that last value, when k is 6, we'd get 12. And if we added up every single one of those values for the different terms that they request from 3 until 6, the sum here would be 36. And this would be called a finite sum. There is a set number of items that you were asked to add up, and they came to a single numerical value. We aren't going to do sigmas to do our adding up because we're talking about adding up larger quantities of things than 4 or 5 items. So what we've been doing so far is Riemann sums to try to add up every single part of the area between a curve and an x-axis. And so those Riemann sums that we've been doing are a method to sum the areas in order to see what happens if we had those rectangles infinitely small on the bottom and infinitely many of them. So calculus says that we need to decode some of this notation and turn it into simpler notation, and we will in just a minute. But this is how they'd start. They'd start by saying that the sum of those n rectangles is equal to something predictable. It would be equal to the limit so that we could make the bases of those rectangles infinitely tiny. So as the bases for our rectangles get very small, we will then have the number of rectangles getting very large. This yellow part, that sigma notation, is actually adding up all the functions values. Well, all the function values were the heights of all of our rectangles. So it's adding up all the heights just like we did in order to get a Riemann estimate. But there'd be more heights. Every single value of the function at every single x value would be used as the height of a very skinny rectangle. And then this delta x, that's actually just our base size. If all the rectangles have the same size base, it's how much x changes by in between those two values. It tells us the length of the base to get the area of the triangle. So it's saying that the sum of the rectangles should be the limit as we make tiny ones out of height times base, all those rectangles put together. If this limit exists, and you know sometimes limits don't for different functions, then no matter how we split up that area, rectangles, eventually we'll do trapezoids, then it's going to be said that the function has a definite integral. And a definite integral means that there is a finite sum. When I add those up, it comes to a number. And if that's going to be true, that between two places on a curve, that area is going to be able to be found by that limit, then we say the function is capable of being integrated or it's integrable. And that's not a word we toss around that often. This screen says the same thing we said on the last screen, that if we take a part of a function on a closed interval, any part of it that we can actually have this limit come to a number, there is a finite sum then, that area can be found, then we have an integrable function there over that interval, and it's called a definite integral because it's defined from one value to the other. There will eventually be indefinite integrals where we want to know the area under a curve from negative infinity to positive infinity. But let's start with one thing at a time. So there's a few existence theorems, and they're ones that we really just need to understand what they say. And we've had existence theorems before. Existence theorems are a little bit buggy because what they tell us is if a condition applies, then something happens. What you should never make out of them, though, is they don't say what happens if the condition's not met. It tells us nothing. Okay? So this one that you have here says that all continuous functions are capable of making an integral. That means between two places on a continuous function, I should be able to get the exact area. So looking down on my first curve that's continuous, that nice polynomial between a and b, because this is a continuous function between those 2 points, might not be continuous elsewhere, but it's continuous between a and b on this curve, that then there is an integral value. It is integrable. I would be able to get that exact area, and therefore, because this is a continuous function, it has a definite integral. Continuous over a to b, and our existence theorem says, you know what, if that's true, if it's continuous between those 2 points, I can conclude that a definite integral exists. There is one number that can describe that area and then have that meaning that we've been talking about. Now, there are plenty of continuous functions to work with. You'll also work with some that are not continuous, that have some discontinuity. Like this is that greatest integer function that we called int x, and sometimes it was written this way. Okay, that greatest integer function is not continuous. It's got jump discontinuity all over the place. However, between a and b, could I break this into rectangles and get an exact area between the curve and the x-axis? Yes. But that doesn't mean that all discontinuous functions can do that. So we just want to be careful. The existence theorem tells us what happens if it is continuous between those 2 values. I will be able to get an integral value, a finite sum that tells me the area between those. So switching some notation around, because that sigma notation is really bulky and hard to work with. So to switch that sigma notation around, we just have to understand where the rectangles come out. And Riemann said if I add up the areas of all my rectangles, I should get this value. So here's what's Riemann saying. Here's all the heights of our triangles. Here's all the bases of our triangles. And he'd like us to add it up to get a sum. Leibniz's notation, though, is the Roman notation, and it's what we're going to use. We aren't going to use that sigma notation because that's got uses for other things. So Leibniz's notation uses this kind of neat Roman, and it is an S-curve. Okay, and what it tells us is from what's our lowest bound that we're looking on the graph and what's our highest input. Where on the graph on the x-axis are we limiting this function? The function that we use to generate the curve then is called the integrand, and it would go in. And that would be all the heights for our rectangles. And then dx is really just a shift off that delta x. That's our change in x. That's really our base lengths. And it's often called the variable of integration. Along that axis, what are we calling the lengths of the bases of those rectangles? When we evaluate this and get a number, then it'll be said that we evaluated the integral. So we're going to practice doing some of those things. Your rectangular approximation is one way that we can estimate the value of an integral. You've also done finding exact area if it's a triangle or a rectangle, and then we can find the exact integral value. So first, let's just practice switching up some notations. They're letting us know that these functions will be able to have an integral value. So they would like us to switch from this bulky notation, the limit notation that we know is taking the limit as the rectangles become infinitely many in number and infinitely small in size. And they would like us between the numbers 1 and 4 to write it as an integral. So the integral symbol will come in like I've got. We need to know our lowest bound, meaning our lowest input is 1 from left to right. So it's really our left to right values. Sometimes those numbers are not smallest to biggest. And then what's our function? What are we integrating? What's our function? If I come over here, they said 1 over inputs that change. So 1 over x values. X will be our variable of integration then. X will be what's changing along the curve. dx. So 1 over x is the function, the integrand, where we get all the heights of our rectangles. And x is our variable of integration. It's where we get all the bases for our rectangles. And that's your final notation. So let's try it on this next one. Why don't you pause the video, see if you can switch it into that notation and come back. If you're back to check that your integral notation from left to right bound with the function that you're using for heights of your rectangles and your variable of integration, x, that we're using as our inputs. That x could be thetas, it could be all sorts of things. So whatever this function is using as its inputs is the variable that your delta will be written in. So let's put this all together. We've talked about areas, we've talked about some notation, and this will take some time to get used to, and you will. So there's two rules in here that go to combine the two, the notation and the idea of the area. So in the first one, it's a definition. It's telling you what this actionable definite integral thing means. Here's what it says. If the curve is non-negative, so you've got this nice non-negative curve, it means that that curve is not ever a negative number. Doesn't mean it couldn't be 0. It's just not negative. And that's the condition we're looking at first for this definition. That means between the curve and the x-axis, all of our area is above the x-axis. And if I could find that area in there, that area above the x-axis is the exact value of our integral. So the integral of the function from a to b, as long as it's all not negative, is exactly the same as the area. Then there's this other part, and they say, but wait a minute, what if the area isn't above the x-axis? What if the area is below it? So they're saying when a function is negative, that means every single output of this function is not above the x-axis, or 0, where it touches the x-axis, but it creates this space below the x-axis. Then if we find area, area is always positive. But that has some meaning as far as what our relationships are. So here's where the area and the integral have a slight difference. Area is always recorded as a positive number. So if I got the area of that space under the curve, it would be reported as positive. However, the integral is going to be the opposite, meaning it's going to be negative. So the integral value is negative down here. So for instance, let's say the area under here was 5. Then we would report the integral as -5 because that probably means a loss in production, a loss in miles per hour, a distance that was in the opposite direction, and therefore we want to know that that counts differently than positives. So if the area is above the curve, then the integral and the area are the same number. If the area is below the curve, then the area is positive, but the integral is negative, indicating its location below the curve. Integrals always tell a net sum of area, and net sum we've been talking about this week means it counts areas that are positive as positive in the total. Areas below the x-axis, it's going to count as negative, so that it gives us the resulting combination of all of those. How much change has occurred? So when we go to calculate a few of these integrals at first, they're going to suggest that you use the graph so that you can see where the areas are above the curve and where the areas are below the curve. Some of the graphs they'd say you should be able to make by hand, and then some of them you'd be looking at a calculator graph. These two you should be able to make by hand. These are both constant functions, and with constant functions you've seen quite a few. So this first one, your integrand, your function that we're looking at, is f of x is y equals -10. So it's that nice constant function below the x-axis. So if they would like to know the integral from 0 to 3, I'd be looking at, from 0 till 3, I'd be looking at the area right in here. The area is below the x-axis, so as soon as I find the area, which will be a positive number, I'm going to have to take its opposite to report it as the integral value. So the area of this rectangle is 3 times 10, 30 square units. His area is never negative. However, the integral is always going to be negative if that area is below the x-axis, so we simply report our integral value then as -30, indicating that those 30 units of area are completely below the x-axis, or the sum of them is more negative than positive. The second one then, they just want you to get used to working with constants, so this one with pi. So if pi is your function across the way, that means your y values are always around 3.14. And if I went from square root of 3 until square root of 27, square root of 27, just so we can think it through, is square root of 9 times square root of 3, or 3 square roots of 3, that may help. And they would like us to find the net sum of area between the x-axis and here. This happens to all be positive, again, that nice constant function above the x-axis. So that rectangle's area, or realizing that that's what we need to calculate, is that distance is rate times time kind of idea, is that base is going to have to be 3 square roots of 3 minus the square root of 3 to find out how long it is between those two bounds. and then multiplied by the height, which is pi. So we've got 2 root 3 times pi. Since it's all above the x-axis, the integral value is the same. And therefore, when we go to report the value of the integral, we're going to give the exact same area because it is positive. So 2 square roots of 3. And sometimes you put the pi in with the 2 just to make sure that nobody thought it was under the radical sign. Okay. All right, 2 more. Using the integrand, they gave us the function and the graph to help us out so that we can see when we have area that should count in our integral as positive or area that should count in our integral as negative. They're letting us look at the graphs. So they gave us that the integrand here is this nice function y equals theta. So that means that we're not in x's anymore. Our variables are theta and y's, or theta and f of x. So that d theta is telling us that we've got a different input variable here. And don't let that throw you off. Okay. So when I go to look at this, I'm trying to find the integrand, or the integral, sorry, between pi and 2 pi on this curve. I can see with my eyes, that's all I'm using, that the area is above the x-axis. So if I find the area, that will be the exact value of the integral. So now I'm going to go calculate that area. It's a trapezoid. The trapezoid is turned so that really this is like the height of the trapezoid, which is pi. And these are the 2 bases. Now, I should probably go find those ordered pairs so I can find out. If I put pi into this function, it outputs pi. If I put 2 pi into this function, it outputs 2 pi. So this section is 2 pi in height. This section is pi in height, using those y values as our heights. Those really turn into the bases of my trapezoid. So trapezoids are 1/2 sum of the parallel sides that count as their bases, and then times whatever the height is, which in this case is that pi. So we have to kind of turn it 90 degrees to see it with its bases as bases. So as I do that, my value here is going to be, it's going to be 1/2. Bring that pi over here, and then there's 3 pi total inside. So 3/2 pi squared would be our integral value. So if I can calculate the exact area, I have the exact value of the integral. I don't need Riemann sums them to approximate. I've got exact values through geometry. This next one, the graph shows us that we've got an absolute value graph here. They would like the integral between 3 and 6. So between 3 and 6, I first get some area here between the x-axis and the function, and then I get some more area in here. The first part between 3 and 4 is actually going to count negative in our total, between 3 and 5. So what we really want to think about is getting those areas separately and combining them with their signs to get the value of the integral. If somebody asked for area, we'd add them both up as positive. But if somebody asked for the integral, it's the net sum. And I see more negative area that will count in our integral than I see positive. So I'm expecting my integral value to be negative. So in that first stretch, I'm going to count that as negative area. And I'm going to count it as 1/2, a base of 2, and a height of 2. The next one I'm going to count as positive area because it is above the x-axis. So 1/2, 1 times 1. The net sum then is putting both of those together. So there was negative 2 square units worth of area below the x-axis, positive 1/2 above. So negative 3/2 is the value of that integral, because that's the net sum. There is more negative trapped between the x-axis and that curve than there is positive over that interval. Your calculator can get into play a little bit to do some approximations for integral values that are definite. So anytime the book refers to NINT, they're referring to the numerical approximation of the integral. This does not replace you being able to do this. This makes it so that for really icky functions, ones that we're not going to take the time to go break into rectangles or find geometry formulas for, that we can get an idea what it should be. Your calculator is not a perfect numerical integration tool. We've seen that before with other things, that it doesn't calculate perfectly all the time. It's also going through some things of breaking it into smaller parts and trying to come up with it. So go to your calculator and insert that function into your y1. Or you can just type it in separately, but otherwise, if you put it in your y1, we'll be able to use it in place of that. And your curve roughly, and again, we don't have to see this necessarily, but your curve kind of looks like that when you graph it. And between -1 to 3, they're looking for, since it's continuous, there is an integral value, a definite integral that comes to a finite number. We'd like our calculator to approximate it so that we're not going to do all the rectangles on this one. So if you go under the math key on your calculator, option 9 is the integral approximation. And it should pop this notation into your calculation window. You're not in the graphing anymore, you're back on the main screen. And it's asking you basically to enter the values that you'd like to do the integral for. So you could either enter the lower bound -1 to 3 and then type the function in as I did in this screenshot. And then after the parentheses, you have to tell it dx, so that you're telling it the variable. Otherwise, if it's in your y1, you can ask it for lower bound of -1, upper bound of 3 of y1 dx, and it will calculate, and it takes it a little bit to do this. Okay, and if all's well, the number that should pop up on your screen when it approximates should be around this, and sometimes they're a little different depending on the operating system on the calculator, meaning in those last decimal places. And what that's telling us is that approximately, that would be about 1.3 decimal places for AP Calc, that would be the area under the curve's net sum. So when the book asks you for the NINT, or sometimes FNINT, you realize that they're asking you to use your calculator and get a numerical approximation with technology help. So your tasks in 6.2 day 1. Okay, the problem numbers are here. For 47, we just like a rough sketch. You use your calculator, so please pay attention to ones that are not grayed out, meaning you could use your calculator to see the graph and to help you out.